honored pleasure today to have Dr. Sonika Robertson, who is the Territory Sales Manager for Instruments, to give us a talk. She was awarded a Bachelor of Science, Master of Science in Physics, which is outstanding. Of course, you people would appreciate that, you're chemists. From the University of Delhi, and she got her PhD in Mechanical Engineering from the University of Houston. Her doctoral research was on mechanical and microstructural characterization of thermoelectric ceramics and reactively glazed metal ceramic interfaces. Upon completion of the doctorate, she worked as a metallurgist and failure analysis engineer. Seems to be about what half the people go into is failure analysis. Good jobs. And then she worked for Leica as a Leica microsystem in applications of optical microscopy, and recently has joined Oxford Instruments. And she's going to bless us today with a talk about high-resolution spatial EDS and EBSD. Now, the electron microscope group is an acronym society. So EDS applies to energy dispersion spectroscopy, which tells you what elements you have, if you know what you're doing, and you can sort of get a quantitative analysis. EBSD is electron backscatter diffraction and has to do with crystal structure analysis. So you can get the elements and the structure. That's pretty unique. The better thing about this, we have all of this. So come see us. See Rebecca or me about doing this. And now I'll turn it over to Sonia.
Thank you, sir. So I'm assuming most of your graduate students forced to sit through this. Oh, lovely. This one person. That's okay. I did that for my PhD. So today, if you're expecting a sales pitch, not going to happen. It's also not a training. My goal here is to share with you the capabilities you have, how far technology has come, and I'll give you some examples of when I started my grad school and doing SEM analysis, what life was like. This makes me want to go back to not go back to grad school. Once PhD was enough, but I would love to reanalyze my samples with the tools. Let's put it that way. So how many of you that I can see do SEM analysis? Ooh, there's a few hands. EDS, EBSD. Okay, lovely. So as Troy mentioned, we'll talk about high spatial resolution. Talk is divided in 3 parts. First one is just general introduction to the technology, the advancements, what you have here. And then second part, which is where I will spend most of the time, is how you push the resolution limits. And when I say resolution, I'm not talking about making the peaks narrower. I'm talking about just mapping nanoparticle scale features or just finer things in the SEM. Of course, you have TEM too, but that's this chart. And then at the end, it's extending the same discussion to how you would do high spatial resolution EBSD analysis, which is mostly you're dealing with deformation on very small scale, length scale, or you have very fine grained materials and how you would go about characterizing those because standard techniques may not allow you to get useful data. Okay. This is what will look familiar when you do end up going to the SEM lab. The guy on the left is the EDS detector that you will not see because it's directly on the opposite side of the column. So you'll have to peek from either side to see it. It's hanging off the system. And the blue box, don't take it as scale because the blue box is much smaller than the detector. It's somewhere, I don't remember seeing it underneath, but it's what controls the system. And what you have is Ultimax 170. It's essentially a 170 millimeter square detector. Sensor size is that dimension. And I want to mention that's the largest in the world. There is no EDS detector with a sensor bigger than that, which obviously means you have very high throughput. To give you an idea, I grew up with a 10 millimeter square. So you have 17 times bigger with newer technology. So you can afford to go faster and not have to spend a whole day doing a single map, because that's what my life was like. And mine used liquid nitrogen. So when there was a shortage of liquid nitrogen in the city, you couldn't do EDS, or even in your research store. You don't have to deal with any of that. It's Peltier cooled, so it uses thermoelectric materials and the reverse operation, Peltier cooling. So largest detector, it's not just the throughput that you get from it. What else you can do? Normally, I don't know if you all remember, my life was go to the SEM, collect the secondary backscattered images. You're looking at those based on backscatter. You can kind of tell heavier elements versus lighter elements. Maybe there's some differences. Now I'll go to EDS and collect the data. And I can't tell you how many times the result was, this is useless. I wish I could just have like a real-time map or that information as well. Well, now you can. So the new system with the large detector, as you're moving across your sample in the SEM, you'll have secondary backscattered images. Well, not images, but it's the live feed. And on the other monitor, if you look, you will also have real-time X-ray data. So you will have that as you move across, and you can optimize. If you stay longer at a particular spot, it's just collecting more counts, and so the resolution will improve, but you don't have to now waste doing EDS analysis where you don't see anything of importance. You could just hang around, see what the better resolution gets you if you wanted to, and decide, you know what, this is not worth doing the EDS analysis on. I wish I had that. Okay, and you also get the spectrum at the bottom. So that's one of the advantages you get with the new system, is real-time chemical information that you'll have for your samples. The other thing, the high throughput I mentioned, and this is not the raw counts, I'll mention what TrueMap is, but with this system, we analyzed a slag sample, and typically you could get 1.5 million count rate, which is a lot, but you can collect element maps like that in a minute. And so I told you it would take me half a day to run something. Even a 45-minute makes such a huge difference. It like makes everything pop out. So you have those capabilities here. The TrueMap thing I mentioned that I discussed with Rebecca and Roy earlier today, it's one of those things again. Once I learned what it could do, I do wish I'd known it sooner. But normally, when you get your X-ray maps, you're looking at spatial distribution and you might go, there are overlapping peaks. I know that this distribution should not be this way. Maybe there's some background influence because one element is a lot heavier, the other one is not. So in that, you also have the option to get true maps, which you could do post-processing or real time. It just slows it down a little bit, but it would try to remove any false variations due to your background, any artifacts, any overlapping peaks, and you will get true spatial distribution. And here's the example here. I love this bit. Tungsten and silicon overlap. Normally, you will end up with a map like this. You have to know your materials, and by the end of your SEM EDS career, hopefully you'll remember the periodic tables and you'll go, you know what, there's an overlap between those two. Because the system on its own, it'll get you only so far. It's better to know more about your materials and these kinds of things. But with TrueMap, it actually shows you the true spatial distribution, because it's not looking for a single peak. It's trying to look for, this element is supposed to have multiple peaks. Are those there or not? So when you have that, when you're not sure, actually, after I learned this, I only used TrueMap. Same thing with the line scan, because you can see the obvious differences. And I know it won't be a training, I told you, but this is too important to not mention because it did change how I was running the analysis. So you will see that for your line scans and for your element maps. So that's something you can check out, and I can get you more information, or Rebecca and Roy can, but I'll help them. Okay. Well, by the way, I have a lot to learn. I only know some things about the Oxford systems, so practical side of the high throughput, I know historically the issue always has been, I don't know if you know this, my gray hair should tell you something. I've spent a lot of time doing this, but the historical issue, not as long as Roy, the historical issue was always, if you go to higher count rates, can you even process those? You could have multiple photons arriving at the same time. How can you be sure this is coming from this particular X-ray or this element versus combination? What's called like some peaks. I don't know if you've run into those at all, but there are nuances when you're doing the analysis. So historically, high throughput, you could crank up the voltage, the beam current, you could get higher throughput, but could you process it? And your dead time goes through the roof and you end up saturating the system. The point with the newer technology is the max resolution, which is the peak shape. So full width half maxima is guaranteed up to 130,000 counts per second. You can go up to 200. In fact, the data here is showing you between 4,000 and 400,000. The peak shape is not spreading too much. It's more of higher count rates. You end up having more some peaks and other artifacts. So when you're doing the most precise analyses, you'd want to be around like 130 to 200,000. But again, the newer detectors are capable of handling higher throughputs. And you can see this was a standard mineral sample when you can see the quantification at 4,000 versus 400,000. And it varies some. So it depends on what you're trying to do. This is not microprobe. This is not APMA. This is not, again, gold standard for us was always OES, nothing else. But depending on what you're trying to do with the system, it's just something to keep in mind that you can push the limits a lot more than you could historically. Okay, 3 modes of operation in an SEM, because ideally when you're doing high resolution, you could just go to a TEM. I wanted to, but the amount of money I had would get me 2 TEM runs, no extra samples, or 40 hours of SEM work. So I was limited and ended up using everything I could do on SEM, which is why I wanted to share with you what's possible, because we're not looking to replace the TEM workflows. It's stretching what you can do on an SEM because the sample prep isn't as complicated. You don't have to spend so many hours in the dark room and it costs less. But again, you have the technology. I didn't. I'm just making up excuses because grapes are sour because I didn't get it. Okay. Normal analysis is high kV SEM. This is what you'll call like 20 kV, 15, 20 kV. There's the low kV SEM mode, or you could do what's called STEM SEM. So STEM, but not in your TEM in an SEM. So as I mentioned, this is what we use the most often. In fact, I worked in a lab briefly, I visited a lab briefly where there was a note behind the SEM saying, do not change the voltage from 20 kV. You don't ever want that. Because those people, I don't know what they thought, if it's going to destroy the machine or something, but they weren't realizing that depending on what you're trying to do, you will want to vary the voltage. So what happens at 20 kV, typical working distance 10 to 15 millimeters, your resolution is limited by the probe size, so you have just larger probe size and you're sampling a lot more volume of the material because your 20 kV electrons, again, they're interacting. There's a finite volume down here which limits your resolution in an SEM, even with the latest technology, like 30 to 50 nanometer features is what you're capable of resolving with EDS. This is not talking about what you can see in an SEM. This is strictly doing X-ray mapping. The low kV, for me, and again, for us at Oxford, anything below 10 kV, we're considering low. Again, it depends on what materials you're characterizing. You talk to nuclear people, they deal with uranium a lot. They wouldn't go below 5 because you're sampling like single-digit nanometers because uranium is so heavy. So low kV, anything down to 1.5 kV I know I would laugh 10 years ago. Now it can be done. And your working distance ranges from 8 to 4 millimeters, and your resolution is now still limited by interaction volume, but it's smaller than it would be at 20 kV or 15 kV. And you can go down to characterizing 5 nanometer features. I know it sounds crazy. I'll show you some results too. The STEM mode in an SEM, we're not doing, again, 200 kV, what we would do in a TEM. In an SEM, you can, though, go up to 30 kV, and your working distance, again, 6 to 10 nanometers, and this time, your spatial resolution is limited by the sample thickness, because when you're doing that, the transmission mode in an SEM, you're still trying to get an electron transparent sample. So reiterating that with interaction volume. So this is example for ion at 20 kV. You can see the kind of interaction volume just from Monte Carlo simulations. And that's something you can do. You can check to kind of better understand what you're dealing with. I had to, because I was working with biomaterial interfaces a lot. And so there's a lot of changes because you have heavier elements on one side and lighter, and there's a combination. And so you just need to keep in mind what you're trying to characterize, but this is just giving you a basic idea of what you're trying to do with improved spatial resolution, which is limiting this volume where you're getting the X-ray signal from. Going from 20 to 2, you can obviously see this area is much smaller, this volume. This is an area, but overall we're talking about the volume. We're not talking about reducing working distance on this detector. There's a special detector for that, a windowless. We talked about it and didn't get it because it gives everyone a heart attack when you're too close to your samples. 4 millimeter working distance, and there's no window to protect it. So the risk of damage is higher. So we ended up compromising with the windowed largest detector. And then this is the 30 kV STEM example. If you see, this is not to scale. Don't compare those things. The 10 nanometer part is right. But again, because the sample is so thin, it doesn't get enough time to spread in volume. And that's what's helping improve your spatial resolution with the probe current, the smaller probe current. Well, that's 30 kV. So next data, or next few slides, I will show you results on low kV and then some examples on STEM, because when low kV is not enough, I forgot to talk to you about if you have like where you go for dual beam analysis, but being able to get lamella and doing the analysis on the same SEM with the EDS detector will allow you to further push the resolution limits for X-ray mapping. So this is the kind of data that you can get. And I know it doesn't look the most impressive until I highlight one. This is all low kV. So these are different detectors from Oxford, but you're going down from 7 kV to 5 to 3.5 to 1.5, and this is that windowless I mentioned. The scale bar is 10 nanometer thickness of these donut-like features. These are NAND gates, semiconductors, and then you're looking at lighter elements, except for tungsten. So there's nitrogen, oxygen, and silicon. And the acquisition time for these is somewhere around 30 to 45 minutes, depending on which one you're talking about. So with the solution you have, that's this one, orangish, you're able to characterize features down to 10 nanometer dimensions, even at the lighter element side, even at 3.5 kV. You can map those. But again, the system is what you make it to be. Don't just rely on auto ID. It's a great starting point, and you can improve the results you're getting by keeping in mind what samples you have, checking a bit more about like the periodic table, even having discussion amongst yourselves or with Roy and Rebecca, because you can definitely improve the kind of results you get when you know a bit more about your things. Professor Mean, he was the one who taught me EDS analysis at University of Houston. He passed away a couple of months ago, but he had printed this huge thing and laminated it and put it above the SEM wall, like in that room, that said, "Don't ask me how that element got in there," because that will happen all the time. And he just encouraged us to learn more about our materials, maybe how we're preparing the samples, possible sources of contamination, because all of that will show up in your SEM, especially when you're doing high spatial resolution analysis. So the more you know about the process, the more you know about your samples, the better results you can get on that system, because you do have the largest and one of the best systems I've ever used, hands down. Example data, this was like a 70-minute acquisition. There are 30 different fields of view stitched together. 640 million total X-ray counts. That's a lot. And this was done at 12 kV, by the way. And you could zoom in. This is 100 micron scale bar. There's aluminum, nickel, iron, silicon, and magnesium. And you could further do high resolution at 5 kV just in 4 minutes with that detector. So you're able to characterize, again, scale bar here is not that crazy. It's only 10 microns. So let's go to crazy. This is sub 20 nanometer features, again, characterized with the same detector. You're starting to see the pixelation show up. But remember this one rule. If you can't see something in your SEM, you can't do X-ray mapping on it. So you need to do a good job of focusing on the SEM side as well, because that will allow you to improve the results you're getting. This one was at 1 million X magnification, and at that point, you will want to have drift correction because you're at a really high mag. But here's another example for tissue. I don't think anyone here deals with it, but in case you ever do, hey, you have the tools to characterize that too. Because with biological samples, again, the requirement is low kV, and that was historically just a challenge because at low kV, we're running into issues of, well, even my 20 kV takes me half a day. So what am I supposed to do? Dropping down to 5 kV, like spend a couple of days just doing that? It just was not practical. But that's not the case anymore. Okay, this is some of my favorite data here. So on the left side, and this is different. So Roy, Rebecca, forgive me for this one slide. This is with a windowless detector. I just wanted to show you all how far technology has come. So I've been talking about 3.5 with the window detectors, and it's because if you go any lower, the window itself blocks some of the signal. That's the issue, that you can't go anywhere lower. But when you remove the window, you can go lower. But again, for the kind of work, if you need this, you go use the TEM. So when you remove that with the windowless, this is a processor cross-section, and you can see this layer. Granted, it's tantalum, it's heavier. It's still 4 nanometers wide, and this magenta color here, this is actually the nitrogen layer. So that's the lighter element that you're seeing. Scale bar, 500 nanometers here. Now the right side, I love this thing. This is single layer graphene sheet on silicon substrate. The darker regions are where the graphene sheet's folded over itself. Could you imagine doing 1 kV mapping? Normally, when you do a carbon map, you just get nothing because you can't pick up the very low end of the spectrum. But at 1 kV, we could, after removing the window, of course, and being closer, we could map this single layer of graphene sheet, and you can actually see areas where it's folded over itself because you see increase in carbon intensity, which if you told me 10 years ago we could do that, I would just laugh and leave the room because I would think I'm crazy, or you are. Okay, so we talked about some STEM analysis too. STEM does require more work. You have to prep the lamella, but you don't need to worry about anything else here, just this table. So our product manager was kind enough to educate me on this. This is just complete theoretical X-ray generation study. So we're not looking at anything else other than how many X-rays are we generating, what kind of counts we can get with typical acceleration voltages. So in a TEM, you'll have typical 200 kV, and look at the count rates. You get a certain signal, but the issue is at such high energies, you have a lot of the electrons just passing through, and there's not enough time for them to interact with the material. So the X-ray generation is actually limited. Now, if you go to the other extreme, 2 kV, you get nothing on the higher energy X-ray lines. You get decent counts for the L alpha lines, you can see right here. But what's the issue? You can't excite anything above 2 kV. You're limiting yourself. If you're using 10 kV acceleration voltage, you will not have lines higher than that. So at 2 kV, you won't have anything higher than that, which is not enough depending on how complicated the material system is that you're dealing with. So if you look at 30 kV though, there's actually 3 times almost counts than what you would get in a 200 kV STEM TEM analysis. It seems to suggest that you could get away with like doing the same count generation on a TEM will require you to have 2 to 3 times the solid angle or 2 to 3 times the detectors to get that. So what this prompted was a comparative study. Same sample, it's the nickel superalloy. Your chemistry people, I don't know if you deal with this. Oil and gas industry, aerospace, we use a lot of superalloys. I say we, I left that job. But so nickel superalloy has these nanoprecipitates, the gamma phases, and these are 10, 20, 30 nanometer large features. So this is, you would only do TEM studies. All the textbooks you would find historically, they just talk about TEM analyses to characterize these, to see these. Look at the low kV. That's possible. I know it's not as crisp of a resolution, but I just couldn't believe that you could even start to see the structure of these features that are this small. And then 30 kV SEM, it's a lot improved, and the resolution is similar. Again, it's not to say, don't kick me out just yet, it's not to say that your 30 kV SEM replaces TEM. The point is, you can push your resolution on your SEM systems a lot further these days with the improvement in the technology, which may enable you to maybe save some time, do more sample analyses, or if you have any limitation on resources, again, it's worth trying to see what you can do. And then again, when you need the ultimate resolution, you will end up going to the TEM anyway. Okay, switching gears. This was EDS side. For the few who do EBSD, this is what the detector looks like. Again, I mentioned you can't see any of that. I walked in and was like, did they forget to put it here? Because I can see the software. So if you walk into the room, you'll see this would be the front side. This is the column, and on the back side, there's the EDS on top, just schematically showing you how you end up doing simultaneous EDS, EBSD, and this more horizontal, closer to horizontal, is your EBSD system. That's also set up here, CMOS-based, full megapixel resolution that you can get with it. It uses fiber optics coupling, so improved sensitivity. I know these are just words you don't care about until you go in there with finer grains, and then you will start seeing the benefits. And there's a proximity sensor that we were just discussing. So if you're about to crash into the sample, a warning goes off and the system is stopped because we want to make sure you don't destroy that equipment. So there is a proximity alarm sensor that whether if it's a stage moving that gets too close to the detector, it's going to stop that, or if it's in the movement of the detector, it'll retract that. So that should help out, prevent collisions. But please pay attention when you go in there. If you're inserting EDS detector or EBSD, because they can be expensive. Okay, so because you have a full megapixel resolution camera, you can actually get full, you can do high resolution EBSD analysis. You can do kernel average, like localized deformation. You have finer grains, you can study those. I'm talking about like 50, 100 nanometers. You can do that. You have the system to do it. Now, I don't know if you run into that, but you can. And when that's not good enough, because that always happens, push the limits. Transmission EBSD, if you go online, some may call it TKD. And if you try to find the original papers on it, it's by Dr. Geis when he was at NIST. So you could actually, you're so lucky, you could have him just teach you transmission EBSD. And when you do that, just flag me down. I'd love to attend too. So again, the point is, in this case, you're again making a lamella, you're making an electron transparent sample, and it's allowing you to, and you're using still higher acceleration voltages. I'm not going to claim to know too much about it, but same thing, it allows you to improve the resolution. So you can go down to 10, 20 nanometer grain sizes to characterize or get better results on deformation studies too. So here on the left side, you're seeing a phase map and high pressure torsion deformed duplex steel. Right side is the orientation map. So the different colors, these are different individual grains. What happens if you don't try to do things like that and just use normal EBSD mode? You'll just get black everywhere because there aren't enough pixels being picked up in individual grains to give you any useful information. That's why this whole crazy thing about how do we improve the results we can get on the systems. And with transmission EBSD, there are different geometries. So Oxford uses the off-axis geometry. So if this is your electron beam coming through this gun column, this would be your sample holder. This little red thing right there is your lamella, and your EBSD detector is right on the side. So you're getting the signal generated like from the underside of the lamella. That's what you're doing. A few months ago, Oxford just launched an add-on. It's an attachment to the EBSD. So again, point is try EBSD if the resolution isn't good enough, excuse me. If the resolution is not good enough, you go talk to Dr. Geis or study his work and figure out what we can do with transmission, EBSD. And the next step, again, before even going to TEM, is now there's an attachment. So it's now being coined near axis TKD by Oxford. So normally your screen ends up being here at this angle right here. This new attachment allows you, you can install it yourself on the microscope. And so now this is where your sample would sit. The electron beam will come right through, hit the bottom of the screen, and you have improved geometry. What does that get you? 10 times higher sensitivity. So the example data set I have is, this was using the traditional TKD with the off-axis mode, and we were using 5 nanometer step sizes at 10 nanoamps, and now we could go down to characterizing 2 to 4 nanometer features because we could go down to a 2 nanometer step size with the improved geometry. But you don't need to go that far. That's just to tell you that that's how far technology has come these days. And now you can also do EBSD on TEMs with precession electron diffraction. It's different, but again, that's what we can do. So now you know the tools that you have, the things you can do, and when you have questions, you have enough resources here, and I'm always available. And this last slide, I have a few more minutes. This last slide is mainly showing you what Oxford does. I handle just this tiny little part. Everything that goes on electron microscopes, EDS, EBSD, WDS, OmniProbe, that's the nanomanipulator. There's a new thing called BEX, which, since I have time, I'll mention to you. It's collecting X-ray data and backscatter electrons at the same time. And so it's completely, again, changing how we have been doing things with the SEM. Another thing to know, Raman. Does anyone do Raman analysis here? Oh, lovely. So you can also install Raman on an SEM these days. and do in situ. Again, it's not interfering with your electron beam. It's like standalone Raman, but within the chamber, but it allows you to do more correlative analysis, because old school, when I did Raman, you go to your confocal microscope, you do the analysis, and if you wanted to do further analysis, I take it to SEM after making some markers, something to try to find the area. That's what's being eliminated by also being able to just install Raman on an SEM. There's AFM slide that Oxford also provides. The new addition is nano indentation. Don't know if any one of you do nano indentation. Oh, you do everything. My PhD started with working on nano indenters. We had one of the original ones because my advisor is friends with Professor Farr. Got to meet him a few times. And so a few months ago, Oxford acquired femtotools, nano indentation. So you can install that in an SEM2 that's standalone, but you could do in situ as well. There's so many things. We're running out of ports. Like they need to make more holes in it so you can put more things. And then there's magnetic resonance. But that's what Oxford does. I really appreciate the few of you who showed up, even though it was because you're required to. And here's my contact information if there's anything I could help with. But I know you have better resources here already, so I'll work with them and get you whatever you need. And there's plenty of time for questions. Thank you. Oh, you have a question?
The hybrid lens or the super lens? I mean, there's different trace lenses you can use.
Oh, wait, which ones? Are you just talking about the X-ray mats?
Yeah.
So this is all with the detectors you have, except 2 slides, which was with the windowless, which was really low kV, like below 3 kV. But everything else I showed you is with the system here. It doesn't have different lenses. It's a single detector. You're just optimizing the acquisition conditions to get what you need. So going back, actually, this is the perfect slide for it. There's no different hardware for these. You're just changing the acquisition conditions and your samples. So this is what you normally do. You can drop the voltage to below 10 kV and you'll be right here. And you can make a thin sample, more like a lamella, electron transparent, and you'll be in this mode. But everything can be done with the tools that you have here. You don't need anything extra. So those would be, can I find anything? Okay, those would be the black and white boring images. I live in the world of color now. Yay. So those are the images you get from the SEM that use the lenses. Our side is literally, you can change the colors, by the way. So I love Christmas colors, so I would change those, but you can change those however you want based on the features. But this is just X-ray data for each pixel, not really images. Yes.
So this surface analysis, or if you have like I work with soft materials. So if you have phase separated domains where you could have like a silicon containing domain with an oxygen containing domain underneath, does it read multiple layers or just says what's on the surface?
I'm so glad you brought that up because I completely forgot to talk about applications here specifically. So it does what you tell it to do. And by that, what I mean is when you want to study the surface level, you don't want it going, say, below a few nanometers, you will use lower acceleration voltage because that's limiting how far deep you're going. Because the deeper you go, you'll get data being skewed by what's underneath. And if you wanted even better resolution, like you could have, again, electron transparent 50 nanometer, 100 nanometer thick sample, and you'll further improve the resolution. So this is like a tissue sample, and the different colors correspond to different elements. So it will help you separate. These are the oxygen-rich areas. This is where I have something else. But it will do what you tell it to do. If you do 20 kV, some of your samples might not even withstand it. Like with biological, it happens, or some of those might interact with the SEM conditions. So that's part of the advantage is for surface study, you will want to use lower acceleration voltages. Corrosion product, any precipitates you might have, any nanoparticles you might have suspended in a matrix. If you want the really crisp X-ray data, you will want to use lower kV analysis. Sure. Okay, can I get her email so that I could provide her details? So we talked about this. It can be as quantitative again as you know your samples, as you work with it. There's a peer-reviewed study I can share that characterizes this series of detectors that you have here, and it shows that with Oxford's approach, the factory calibrations, even without using standards, you could limit relative errors to down to 5%, which is crazy. But again, it will require more intervention from your side, knowing what samples, what elements you're working with, and making sure that any kind of overlaps, those artifacts are being removed. The sample prep is important at lower kV, especially because I know I talked about this. If it wasn't recorded, I had quantitative data to show, but it's not published. And so I can find specific studies to share with you, but it can go a lot further than it historically could. And I've done that on geological, like standard samples at 7 kV, 3.5 kV. So I can add more to that if I could get her contact information. Or get to Roy and Rebecca and she could reach out to them.
Interesting. Sounds like it's not to get good EDS from these now, but accelerating voltage, etc.
1 micron? Ooh, my memory is failing me here because I don't remember the silicon interaction volume, but I don't think 10 to 20 kV is that crazy for that because we're not looking at nanometers. Even 15 might work. So that's where I would start. And if that doesn't work, contact us because we have a team of applications people that sit next to the microscope. I'm trying to get one, but you know, in sales, they don't give you microscopes. You don't know. There's 2 nerds in our house. My husband and I met during our PhD. We might end up with an SEM someday at the house. We already have an arc melter. We already have like all the welding toys. We have metal powders. We make our own things. We just need an SEM now. Yes, ma'am. Okay. So there will be, as I mentioned, the results might require some intervention from your side if you know what's in it. So the materials I was working with that I tried where it did okay, it was the metal ceramic interfaces, except my ceramic was, don't laugh, okay? Hafnium, zirconium, titanium, cobalt, antimony, tin. That was just one ceramic. It's half Heusler. But again, knowing the concentrations, I knew if anything crazy showed up, I knew exactly what was supposed to be in it because I handled it from the initial process. So I could take a look at it. I didn't struggle with it, TrueMap, but I couldn't tell you like how much of it was because I knew exactly what was supposed to be in it. And my sample prep would obviously involve carbon, and because you will have the silicon carbide grid and stuff, so, and silica, alumina. So it's just more information you have that you can use. It'll help you improve results, but try that. And if it doesn't work, at least reach out to us. I'm in the process of learning, and maybe our applications people have some other tricks. Actually, there are a few other tools in the software. I'm not asking you to just use TrueMap on its own. There are other things that we will use in conjunction with that, but it does a great job when there's clear overlap, like with tungsten and silicon. Now, if you have 20 elements, it'll take longer to process, but again, we're looking at where the overlaps are, because there might be regions with clear distinction. So I can't say without looking at the sample and the data, but I can tell you that there are lots of things you can do with the software to try to make sure that you have more clear separation in your phases, if that makes sense. Yes, ma'am.
Oh, well, I'm not gonna do like my full reportable results. I know I want to take this, 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 like as you're doing the live scan.
I can't remember that, shamefully. But what it does do at the bottom, there's also called a live trace. And I removed that slide because I thought, who would care about that? I shouldn't have. What it's doing is so you can have an overall registered image of your sample, whether it's taken in an SEM or something you took on an optical microscope or even with your phone as reference. But all the areas that you have traversed, it's collecting X-ray data the whole time. And so it's actually filling all of that information with overlaid element maps in that little mini view that you could use, but you'll have to save it as a project because once you close the software, it goes away. But locally, you will have that. And my favorite part with that is it tabulates. So failure investigations, I would spend 5 hours just looking on where something could even be wrong, and then lose an area of interest. It's like, oh, I saw something over here, and then I lost it. And it would take hours to get back. With this one, because it's collecting it the entire time, you could say, show me everywhere tungsten was detected. And it will highlight all the fields of view. And so if there's a particular, like a needle in the haystack, so to say, where it's bright red, for instance, and red's the color for tungsten, you could say move to that field of view and it will go back and you won't have to do that manually yourself. That's an advantage that you get with the live system.
So looking at them post nanomentation, it's not really the capability that one has. Is the the new EBSD have the capability to look at samples that are post machine post indented?
Okay. So my first published paper was nano indentation in EBSD. So I know I'm very intimately familiar with this. What I ended up doing, because I was trying to back calculate elasticity tensor for this material I couldn't get large enough single crystals for. And I had to put, first of all, huge markers like a micron deep indents. And then away from it, I made an array of nano indents that were 150 to 180 nanometers deep. And my grains were small, a couple of microns at large. And then I did EBSD scan. I knew I caused localized deformation, but the software allowed me to exclude those regions by specifying threshold levels. So not just the indent, but even the periphery where you cause more localized deformation. So when I needed to look at just the average grain orientation, I didn't care about it. I'm not saying that's what you need to do, but if it was something like that, that's something you could do. But it's back to the same story. Unless you make extremely shallow indents, depending on what you're trying to study, you may want to do EBSD first because best results still weren't as perfect of a sample as you can get. The more sensitive part just means it'll be able to pick up the damage you've caused, but it will not fix it for you. Now, one of the cool things is you have all the bells and whistles on the software side that you could possibly get with the system here. So there's pattern matching based system that for post-processing in areas where you have poor data quality or just not, you have some discernible patterns, but not enough to index traditionally. You can use MapSweeper to try to improve the data quality. And so that's one of the tools that's available. Another thing is the system comes with 5 four-scatter diode detectors. So normally in an SEM, when you're looking, it's fine, but you do the 70-degree tilt and you can only see part of the sample in focus. With these 4-scatter diode detectors, you will actually see the entire field of view in focus, and you can image those, see what it looks like, and take images prior. But again, it depends on what kind of information you're trying to get while doing analysis with nano indentation, because in some cases it wouldn't matter. Like with me, it didn't matter, but in other cases it might matter, and you might have to run that first. There was another question. I think you have. Okay. Anything else? You all are still awake. Yay. Yes.
Scan.
The time difference?
Yeah.
So time difference is actually not that much. The difference is sensor size. So all of these were somewhere around 30 to 45 minutes acquisition time, but the difference is sensor size. Hence, I don't know why they came up with this campaign, but the name of it was Size Does Matter. And so 170 millimeters square, being the largest, will collect significantly more counts. So you can start seeing the resolution, right? Better spatial resolution of these things in the same amount of time as, say, with the 65 millimeter square or 100. Part of it is the voltage, and the other part of it is the sensor size. So that's where the difference is. Time is similar actually for all of those. Okay. Yes.
On this distance, can measure solids materials.
Like liquids? No. There are different electron microscopes for biological things. Does this have variable pressure or low vacuum? Not environmental. Okay. So definitely still no to liquids, but depending on what samples you're doing, it'll still be solids, but like biological tissues, again, they're prone to charging and stuff, depending on what form it is, right? If it's something that needs environmental, it can't happen. If it can't, basically, if your sample cannot withstand the conditions that the microscope can handle, you might actually be altering your sample and not getting what you're trying to study. So there are different kinds of sample prep you can do even with biological that don't necessarily warrant needing environmental, but again, it depends on what you're trying to study. But liquids is a no-go unless you do like a liquid cell thing. And definitely not silly. Some of the things when I learned, I thought, no, you're joking. I've done EDS, but it's just, we've come that far, everyone in general, the technology, like some of the data I showed you, the surface level, single layer graphene sheet, that's more of, believe it or not, XPS can be very expensive. XPS Auger kind of equipment can be very expensive. So it's not to replace that technique, but being able to still extract more surface level information from the same samples when you already have the tool. No more questions? Ready to go home?